Hi, this is Jim Pollock, and you're watching my lesson on modeling an overland path using the least cost path method for SSCI 599. Let's go ahead and move to the next slide and begin. Alright, first bit out of the box will be the lesson objectives. When you finish this lesson, probably the most important thing to understand is what a least cost path model is, what it can do, and easily more important, what it can't do. And then if you decide to use this method, you really will need to know what data, what research you need to conduct to produce an effective overland model using the least cost path method. Obviously, you should be able to construct a least cost path model using the ArcGIS model builder. But you need to realize that the example presented here is not a cookbook specimen. It's simply a model that gives you a feel for the process. And quite honestly, it's not the greatest model in the world. It could use a lot of work in order to be more effective. But I'll give you some examples from the literature to illustrate the breadth of possibilities beyond this simple example that least cost path modeling has. So if you're ready to begin, please have your handout available, or better yet, read it first, because I'll be referring to it often during the course of the lesson. So what exactly is the least cost path method? Well, when you think about it, it's a way to model freedom. And when you think about that, that's pretty darn hard. If a person is completely unconstrained, he can go whatever the heck he wants, how do you predict his movements? Well, according to the least cost path method, you do it using cost. If we consider this person completely over open range and with no real constraint on his movement, and he's got a choice of two stores for his loaf of bread. One's across a ravine and one's across a straight path. In all likelihood, you'll find him on the way to the straight path store because it costs him a heck of a lot less effort to get to that store than the one across the ravine. Now, that doesn't work if the store across the ravine is giving away bread, or if he's constrained to a path like a road or a railroad. There are other modeling techniques that can address these types of situations. The sample model for this lesson investigates the fall migration patterns, the most likely paths of mule deer in and around Round Valley, California. Specifically, we chose this topic because it's simple, one, and two, it clearly suits at least cost path analysis. Deer are free to go wherever they like, but they need somehow know their wintering grounds during the fall to survive the winter. This particular herd has been highly studied, so there's an abundance of literature on the subject, and it caters very well to the tools available in ArcGIS. The figure at the bottom of the slide depicts our general modeling process that is required to accomplish this sort of model. First step is to analyze the objective. What is the study area? What is the scale? What modeling technique are we going to use? Followed by a literature search. What cost factors drive deer to go in one direction or another? Given those factors, what data can we use to represent those factors into a model? And finally, we had to design and run a model that reclassified those factors into ranked values, weighted by importance, created a cost surface that depicts the cost across a landscape, and then finally created a cost path that depicts our final migration path. All right, at this juncture, I think it's prudent to define some key terms and concepts that will help your understanding as we move through the modeling process. To begin with, we've talked a lot about costs, but in this context, it's probably a very good idea to think of it as resistance. Costs or resistance are factors that lessen the likelihood of a cell to be occupied. In this case, deer. If it's a very steep slope or somewhere he doesn't like to be, it's going to have a very high cost, a very high resistance. Secondly, we have the cost scheme. And this really are your modeling choices and how you're going to represent costs and categorize them so that they're comparable to one another. For instance, later in this model, we'll compare slope to snow moisture content. And a score of 2 on a slope should be equivalent in resistance or cost to a 2 in snow moisture content. Next, we have a cost surface, and that's simply once we've classified and defined all of our costs, we squish them together into a single layer that represents the total cost in each cell. The value in each cell will represent a relative cost to the cell next to it, and on and on and on and on. The cost distance is a raster layer that moves beyond the cost surface to where it's a cumulative distance that starts at an origin, say the migration start point, and radiates out from there. And so you can see how costs accumulate over distance. The least cost path is a single pixel string. It's really what we're after in the end, that connects the least cumulative cost cell to cell between an origin point and some destination or destinations. And of course, the origin and source or source patches are those areas. Those are the areas that we start from, we move to, or move in between, and we create our least cost paths from. All right, now that we've moved through the preliminaries and into the modeling process proper, there are some pre-modeling tasks that must be accomplished properly to have an effective model. And definitely the most preeminent bit that must be accomplished is to define a specific question. Everything beyond here is defined off of this question. And in the context of this least cost path modeling scenario, it needs to be in a to from format. For instance, our question is, what is the most likely path mule deer will take while migrating from their summer range to their winter range? That's a great question, but it's not complete. It's we still need to define, okay, well, what is the study area? What's the context of the question? What is the scale? Certainly, if we have several mountain ranges to cover, these are different costs than if we only have one. Where are the origin patches? Where do these deer or other phenomena come from, and where are they going? You can see in the figure on the right that we have defined a study area. It happens to be based on a previous study on migration timing, so we know that it's legitimate. And the origin patches are the summer range, which is defined by the red area, and the winter range was defined by the green areas. All right, with our preliminaries done, now it's time to get down to the work of finding data that can be inputted into the model. The first thing to find are source patches. This is luckily a flexible format. It could be points of field data with known positions. It could be a vector outline of a habitat, any number of different things. Cost factors are a little more difficult because they have to be raster or derived into a raster, but more importantly, they have to be representative. For us, we didn't know much about deer, so we found a current article and a historical article and looked for the common themes. And what we found was data first snow. Deer are driven down by snow. Couldn't get that directly, so we derived a proxy using snow moisture content. We also found that deer like moderate slopes, so we got a USGS DEM and derived a slope surface to use that as data. And then we also found that deer tend to meander based on how they feed as they migrate. So forage quality is probably a important input. We derived an NDVI from a Landsat scene, and that's pictured on the right. So finally, with solid data in hand, we've arrived at the actual model builder model, and its entirety is pictured there at the top of the slide. I'm going to note at this point that I'm going to keep the conversation conceptual. I'm not going to display any dialog boxes. I'm sure that this audience is more than capable of clicking tool help given the required inputs and desired outputs to determine specific fields that need to be filled out. So the first step is a reclassification. It's the implementation of your cost scheme. This section of the model reclassifies the raw data into a 1 to 9 scale. This is a critical step because it translates slope data, for instance, into a relative travel cost. In other words, it sorts input factors into categories that rank how likely or costly it would be for a migrating deer to occupy those spaces. Further, the reclassification process converts the raw data into integer categories. It's a little strange because the required inputs are ratio, but then we immediately convert them to integer data. But that is what is required for the next step, which is the weighted overlay. The next step in our model is to consolidate the reclassified and categorized data into a cost surface using the ArcGIS weighted overlay tool. The resulting layer represents the total cost for a deer to occupy each raster grid of terrain during migration. The tool also weights each category in terms of importance relative to another. That is, the total cost to travel through a space may be normalized to 100, and each category contributes to a portion of the total. In this case, we assigned snow moisture content 50% influence, while the other two categories split the remaining cost influence at 25% each. We assigned influence in this manner because the literature universally speaks to descending snowline as the primary migration driver. The remaining factors are inferred by us, so the relative importance is really not discernible given our level of process knowledge. This particular step requires an integer input. There is an alternate manner of accomplishing this step, and we'll discuss that in the tips and tricks section. This next step, creating a cost distance layer, is quite significant. It shows us how all the costs line up. But there's a choice to be made here in terms of ArcGIS tools depending on how complex your model inputs are. In this case, we use the cost distance tool, which is the less complex choice. It simply creates a surface that represents the cost accumulation defined by the cost layers we previously made as they radiate from your source patch. In this layer, if you only have one destination defined, one patch, you're finished. This is as far as the analysis goes. The path distance tool is more complex, and it allows for modeling horizontal and vertical factors such as grade and wind. The Mitchell text on pages 231 to 245 provides a good description of these. It's quite complex, but it's worthwhile if it's worthy of your scenario. If, as is the case in our scenario, there's more than one source patch that you wish to connect in furthering this analysis, in creating a actual cost path, at this point it is very important that you create a backlink layer. This layer actually looks for the least cost path and creates a raster layer that each cell actually contains a value that refers to the next link in the path of the least cost path back to the source. This next slide actually contains the cost distance surface that was produced from our data. It's a very important slide. In fact, if you only have one patch, this would be your final surface. You can see on the left where it's very green, this is the source area of where deer are migrating from. And as the deer radiate from this source, the cost increases. The least cost path is actually derived from the path in which that cumulative cost is the least. In this final model step, we create a least cost path. And to do so, we introduce an additional, in this case, a destination origin path, meaning the winter range, the backlink layer, which is used to connect a breadcrumb path between the winter range and the summer range, and then the cost distance layer, which is used to calculate the attributes of the output least cost path. This slide depicts our final results. The least cost path that we're after, and it's no accident that there are two of them, because when you have an output of a model, you need to validate it. And as you can see, there are two of them. We tweaked some of the influence factors to see if they would change. And there are some difference between the two paths, but mostly they are the same, which means that the model as defined by its inputs is stable and reliable. So with the output of our model in hand, I think it's very important to point out that that's a very simple model that we did. It can be very easily expanded and using corridors, multiple sources, and I highly suggest you look up these methods in Mitchell. It essentially means repeating the modeling process and tweaking the parameters to get a wider swath of possible paths, more realistic. From the literature, I wanted to point out, especially Lee et al., this, their model is depicted here, and you can see that really what they did is they changed the order so that they would not have to use the integers as an input. They used integers as an output, which was brilliant because then they were able to use the actual data that they collected and then categorize it into habitat results. The point is not depicted here, but they actually were able to dismiss most topographical factors and simply use their own data. And look in the handout, and it has a lot more details. It's quite interesting. Alright, and with the final seconds that I've got remaining, I just wanted to give a couple of quick tips. We do a lot of processing, and sometimes the layers don't line up exactly right. There's a solution. Change your geoprocessing environment settings to a union of inputs. Just note that certain areas will be invalid where they're missing data. Also, if you really don't like the idea of having to convert everything to integers for the weighted overlay, do it with the map algebra tool. You don't, you're on your own, but you get to use your data. Well, thanks for listening and take care.